So far in this lecture, we've discussed what plate tectonics is, what the different types of plate boundary we have are, and we've discussed a mechanism for how plates, continents can move around the surface of the Earth, and that was seafall or spreading that we discussed in the first module. But what we haven't talked about is what's the driving force for plate tectonics? Why can plate tectonics happen in the first place? And the original idea for what drives plate tectonics is that it was related to large convection cells in the mantle. And many of the A-level textbooks still show this hypothesis. And some of the A-level textbooks also still show that the mantle is molten, and then we've got these large convection cells within it. Well, almost everything about that figure is wrong. So we no longer think that convection in the mantle is the primary driver of plate tectonics. And the reason for that is that although there are convection cells in the mantle, and we can determine where they don't correlate directly with the motion of the plates. So it's not like where we see the largest convection cells, we see the plates moving the fastest. So although convection probably has a secondary role in plate tectonics, it's not the key thing which drives it. So the modern idea of what drives plate tectonics is that it's all related to the density contrasts in the lithosphere. So as we've discussed, at mid-ocean ridges, we have new oceanic lithosphere forming. And at that location, things are quite hot due to that decompression melting. As the plates move away, the new oceanic crust and oceanic lithosphere that's formed will move away from the hot ridge. It will get older, it will cool, it will get denser, and it will sink. So as we go away from the mid-ocean ridges, the depth to the ocean floor gets deeper because the oceanic lithosphere is sinking more deeply into the mantle. And eventually, that oceanic lithosphere gets so deep that when it encounters another tectonic plate, it will slide underneath it. Because it's so heavy, it basically kind of like wants to go down a bit like an anchor. And that subduction process will pull the rest of the tectonic plate along with it. So in this way, the change in density is actually acting as a driver for the plates to move. That heavy, old, subducting oceanic lithospheric plate is being pulled down into the mantle. And this process is called slab pull. And we think this is a really important, if not the most important driver for plate tectonics. There's another driver, which is called ridge push. And this is the idea that at the ridge itself, again, because the oceanic lithosphere is moving away from the ridge, it's getting colder and denser, and it's sinking. The oceanic lithosphere either side of that mid-ocean ridge wants to slip away from it because it's getting heavier, and due to gravity, it's slipping away. So this process is called ridge push in lots of the textbooks, although that's not a great term to use because I think lots of people misunderstand that and think at the ridge the magma's coming up and pushing the plates away, and that's not what's happening. It's not an active push. It's the fact that the oceanic lithospheric plates are getting heavier due to gravity. They're sliding away from the mid-ocean ridge. So probably a better term is kind of ridge slide or ridge glide or something like that. So we've got these two mechanisms, the slab pull and the ridge slide, let's say. We think the slab pull is the mechanism which is much more important because if we look at the speed that the different tectonic plates are travelling, the ones which have the most subduction zones connected to them travel the fastest. So the Pacific plate is very famously rimmed by subduction zones, and it's often given the name the Pacific Ring of Fire. Again, because subduction zones give us volcanoes, so we get lots of volcanoes around the Pacific. So the Pacific plate is the tectonic plate which is moving the fastest of any of the other plates on Earth. It's moving at rates of over 100 millimeters per year. So much, much faster than the average person's fingernails will grow. And we think that's because it's just being pulled really quickly by these subduction zones. Plates which, in contrast, are surrounded by ridges, like Africa, are travelling at some of the slowest rates. So Africa is one of the slowest moving plates at just 20 millimeters per year. And again, it's surrounded by those mid-ocean ridges. So we don't think ridge push or ridge glide, whatever you want to call it, is the primary mechanism, because otherwise those plates surrounded by lots of ridges will be moving more quickly. So we think that slab pull is the most important of those mechanisms. So based on all of this, it's quite interesting to think about what might happen in the future. And because of plate tectonics, we actually don't have that much of a record of the ocean crust of the Earth's history. So the Earth is 4.6 billion years old, and there are rocks on the continents that, have that age. They're 4 billion years old, and we can study them, we can take samples of them and learn about that very early stage of Earth history. With the oceans, the kind of oldest age of the oceanic crust that we have generally is only about 150 million years old. So that's when, Stegosaurus was wandering around. That might seem quite a long time, but in geological terms, that's less than 4% of Earth's history. The oceanic crust hardly records any of Earth's history. And that's because, almost no sooner is it created at a mid-ocean ridge, it ends up being destroyed at a subduction zone, and it gets then recycled into the mantle. The oldest oceanic crust that we have anywhere on Earth is the Mediterranean. So the Mediterranean Sea is a tiny slither where the oceanic crust is about 270 million years old. So it's a little bit of crust which hasn't yet been subducted. So if the plates continue to move in the way that they are, it's quite fun to think about what the Earth might look like in the future. So if everything continues as it has, in the next 50 million years, there'll be a collision between Africa and the Eurasian plate that will completely consume that slither of Mediterranean crust. So although that's a little captured older piece of crust now, it's not going to be around in 50 million years' time. So it's time to get your Mediterranean beach holidays in now, because in 50 million years, that area is going to be a mountain range to rival the Himalayas. The Atlantic Ocean's days are also numbered. So what will happen at some point is that a subduction zone will initiate. Now that oceanic crust is getting so old and so cold, we'll have a subduction zone that will begin to consume the Atlantic. And eventually, probably in about 250 million years' time, we'll have a collision between the Americas and Africa and Europe, and we will once again have a new supercontinent. So that might sound fanciful, but we actually have some evidence that that process of subduction beginning in the Atlantic might already have started. So in 1755, there was a very large earthquake offshore the coast of Lisbon in Portugal. We didn't have seismometers at the time, and in fact, this earthquake is really the thing that kind of started modern seismology and the development of instruments to detect earthquakes. But in 1755, when that earthquake happened, they were very forward-thinking and sent questionnaires out to populations in the area to describe how the earthquake felt to them. And based on that information, and also thinking about how the earthquake felt to people even further away, even in the UK, for example, scientists now have been able to determine how large that earthquake might have been. And they think it might possibly have been as large as a magnitude 9. There was also a devastating tsunami that followed that event, so we know whatever fault that slipped must have been offshore the coast of Portugal to the west. So that's kind of weird, given everything I've told you in this lecture, in that the Atlantic Ocean generally, we have lots of earthquakes and volcanism happening in the middle at the ocean ridges. But closer to the continents, those are areas that are really quite benign generally in terms of earthquakes. We'd expect magnitude 9s at subduction zones in places like the Pacific, but we don't have a feature like that in that area. Some researchers in Lisbon, however, have proposed that what might have caused that earthquake is maybe an embryonic subduction zone that's just initiated. So we might have the beginning of a new thrust fault in the Atlantic that might in the future become the region where we might have subduction of that old cold Atlantic lithosphere that's just began to develop, and that earthquake occurred on that feature. So the race is on to try and find where that feature is, and could it be capable of giving us another large earthquake like that in the future. So on that bombshell for the fate of the Atlantic Ocean, I think I'll wrap up this lecture. So I really hope that you've learned something new and interesting. Go back to your A-level textbooks and make sure that you work out those misconceptions if they have crept in there. And thank you very much for your attention, and good luck in your studies.